For over a decade, China built a fortress in the sky. Thousands of surface-to-air missiles, hundreds of fighter jets, overlapping radar networks stretching from the coast to the interior, all designed with one purpose: keep American bombers out. Beijing's strategists studied every U.S. air campaign since Desert Storm, cataloging vulnerabilities and building defenses specifically tailored to counter American tactics. They watched B-52s lumber across Middle Eastern skies, tracked B-1s on predictable flight paths, and even spotted the occasional B-2 Spirit with upgraded radars operating at wavelengths the stealth bomber was never designed to evade. State media declared the age of the bomber over, claiming that no aircraft, no matter how advanced, could penetrate the integrated air defense network China had constructed. The Great Wall of Radar, they called it, a dome of sensors and missiles that made Chinese airspace a no-go zone for American air power. Western analysts partly agreed. The sheer density of China's defenses, combined with their geographic advantage of operating close to home, meant any bombing campaign would face losses the American public would not accept. The days of flying deep into enemy territory with impunity were over. Beijing had successfully created a defensive bubble that conventional air power could not crack without unacceptable attrition. Then, on a cold December morning in 2022, something new took to the skies over California. Not an upgraded B-2, not a hypersonic missile, but a bomber so fundamentally different it made 2 decades of Chinese air defense investment look like preparation for the wrong war entirely. The B-21 Raider did not try to evade China's radar network. It made the entire network irrelevant. How did a single aircraft design render obsolete the most sophisticated air defense system ever built? And why did the bomber China mocked as just another American money pit become the weapon that turned their fortress into a prison? In 2019, Chinese military journals published a series of articles declaring victory over American stealth technology. The premise was straightforward. While the B-2 Spirit had been nearly invisible to radars operating in the X-band and Q-band frequencies commonly used by fire control systems, it was increasingly vulnerable to low-frequency radars operating in the VHF and UHF bands. These longer wavelengths, measuring meters rather than centimeters, could detect the B-2's large airframe despite its carefully sculpted shape and radar-absorbent coatings. The physics were real. Stealth shaping works by deflecting radar energy away from the emitter, but this technique is most effective when the radar wavelength is small compared to the aircraft's features. When wavelength approaches or exceeds the size of edges, panels, and control surfaces, the aircraft begins to resonate, creating returns that are detectable. The B-2, with its 172-foot wingspan and numerous panel edges, created enough of a signature on VHF radars that Chinese operators could track it, albeit imprecisely. China invested billions in low-frequency radar networks. The YLC-8B mobile VHF radar deployed across eastern China could detect large stealth aircraft at ranges exceeding 500 kilometers. The JY-27A, another VHF system, was positioned on artificial islands throughout the South China Sea, creating overlapping coverage that made it difficult for any large aircraft to approach undetected. Chinese strategists published maps showing the radar coverage, red domes spreading across the Pacific, each one representing a zone where American bombers would be detected long before reaching their targets. The confidence was palpable. One widely circulated 20Z20 article in a People's Liberation Army journal argued that American stealth technology had peaked with the B-2 and that subsequent developments would be evolutionary rather than revolutionary. The author predicted that any future American bomber would face the same fundamental physics problems. Large airframes would always be visible to low-frequency radars, and no amount of shaping could overcome wavelength resonance. The conclusion was stark. The era of penetrating stealth bombers was over, and America would need to find a different approach if it wanted to strike deep into defended territory. Beijing's air defense planners operated under these assumptions, designing their networks to maximize low-frequency coverage while maintaining traditional fire control radars for terminal guidance. The strategy was layered. VHF radars would detect the bombers at long range, cueing fighters and mobile SAM systems to the general area. Once the bombers were close enough, higher frequency radars would take over, providing the precision tracking needed for missile engagement. The system was elegant, proven in exercises, and seemingly foolproof. Russian experts reinforced Chinese confidence. Moscow had deployed similar low-frequency systems and claimed success in tracking American aircraft during operations near Syria. Russian commentators suggested that Western stealth was overrated, that quantity and clever sensor placement could overcome quality and technology. The narrative fit perfectly with China's preferred worldview. American advantages were temporary and adversaries could level the playing field through asymmetric investments. What Chinese planners failed to consider was that American engineers had spent the 2 decades since the B-2's introduction thinking about exactly this problem. The Air Force knew low-frequency radars could detect large stealth aircraft they had known since the 1990s. The question was not whether China would build such radars, but what to do about it. And the answer was not to make the bomber smaller or try to defeat VHF radars through better shaping. The answer was to make the bomber so efficient at its job that detection did not matter, and so difficult to target that detection would not lead to interception. The B-21 Raider emerged from a program called Long Range Strike Bomber, initiated in 2011 with a set of requirements that seemed impossible to reconcile. The Air Force wanted a stealth bomber with intercontinental range, capable of carrying both conventional and nuclear weapons, survivable in the most heavily defended airspace, and cheap enough to buy in quantities exceeding 100 aircraft. Previous bomber programs had failed on the cost dimension, producing exquisite platforms like the B-2 that were too expensive to risk in combat. The B-21 had to be different. Northrop Grumman, leveraging decades of stealth experience from the B-2 program, approached the problem with digital engineering tools that had not existed in the 1980s. Instead of building physical prototypes and discovering problems after millions had been spent, engineers created a complete digital twin of the aircraft. Every component, every system, every assembly process was modeled in software before a single piece of metal was cut. Design changes that would have cost millions and months on the B-2 could be tested and refined virtually in days. The result was an aircraft optimized not just for frontal stealth against traditional fire control radars, but for all-aspect broadband stealth across frequencies from VHF to X-band. The B-21's shape is noticeably different from the B-2. Smaller wingspan, more refined edges, and a fuselage optimized through computational fluid dynamics that allowed engineers to test millions of configurations to find the optimal balance between aerodynamics and radar cross-section. The wingspan, estimated at around 135 feet compared to the B-2's 172 feet, was not just about making a smaller target. It was about reducing the physical features that resonate with VHF wavelengths. Fewer edges, tighter tolerances, and carefully shaped surfaces meant less electromagnetic return across all frequencies. But size alone could not solve the problem. The breakthrough was in materials. The B-21 uses radar-absorbent structures, not just coatings. Previous stealth aircraft, including the B-2, relied heavily on radar-absorbent materials applied to the surface. These coatings worked but required extensive maintenance. Humidity, rain, and thermal cycling degraded them, necessitating constant touch-ups and climate-controlled hangars. The B-21 integrates radar-absorbent materials into the structure itself. The composite skin is not just shaped to deflect radar energy, it is designed to absorb it, converting electromagnetic energy into trace amounts of heat that dissipate harmlessly. This structural approach means the B-21's stealth characteristics are more durable and require far less maintenance than previous generations. Where a B-2 needed 119 hours of maintenance for every flight hour, much of it devoted to repairing stealth coatings, the B-21 is projected to need a fraction of that. The aircraft can operate from austere bases without specialized maintenance facilities, making it far more deployable than its predecessor. But the most revolutionary aspect is not visible from the outside. It is the sensor suite and electronic warfare system. The B-21 does not just try to avoid detection, it actively manages the electromagnetic environment around it, using advanced electronic attack capabilities to confuse, jam, and deceive enemy sensors. When a Chinese VHF radar illuminates the B-21, the aircraft does not just present a reduced cross-section, it responds with electronic countermeasures tailored to that specific radar type, creating false targets, degrading the radar's signal processing, or even feeding back corrupted data that makes the return look like a flock of birds or atmospheric phenomenon. The first flight of the B-21 took place on November 10, 2023 at Edwards Air Force Base in California. The aircraft flew for approximately 2 hours, conducting basic handling tests and validating flight control systems. But even this initial flight provided data that exceeded expectations. The aircraft's performance matched predictions from the digital twin with remarkable accuracy, validation that the virtual engineering approach had worked. Subsequent test flights pushed the envelope. the B-21 demonstrated its ability to operate at high altitude and long range, fly complex mission profiles, and integrate with other platforms through data links. But the most significant tests were the ones that never made headlines: radar cross-section measurements conducted at secure ranges, where the aircraft's signature was measured across multiple frequencies and aspects. The results, still classified, stunned even the engineers who designed the aircraft. According to sources with access to the test data, the B-21's radar cross-section against VHF radars is orders of magnitude smaller than the B-2's, where the B-2 presented a detectable, if imprecise, target to low-frequency systems. The B-21 is nearly invisible. The combination of optimized shaping, radar-absorbent structures, and active electronic warfare creates a signature so small that VHF radars struggle to distinguish it from background noise. Against higher-frequency fire control radars, the B-21 is even more impressive. Measurements suggest a frontal radar cross-section in the range of 0.001 square meters or less, roughly the size of a large insect. For comparison, the B-2's frontal RCS is estimated at 0.05 to 0.001 square meters, already considered excellent. The B-21 is 5 to 10 times stealthier than the aircraft that defined stealth for a generation. The implications for Chinese air defenses are catastrophic. The entire network was designed around the assumption that VHF radars would provide early warning, allowing the system to vector interceptors and SAMs to the threat area. If the B-21 is effectively invisible to VHF radars, that assumption collapses. The first warning Chinese operators would have is when higher frequency fire control radars try to lock for terminal guidance, and by then the bomber would already be in range to release weapons and turn away. Chinese military analysts who reviewed leaked information about the B-21's performance reportedly described the situation as a strategic disaster. One assessment, obtained by Western intelligence, concluded that the B-21 represented a generational leap that China had not anticipated and could not counter with existing systems. The report recommended immediate investment in new sensor technologies and admitted that current defenses would be inadequate against the new bomber for at least a decade. But the problem for China goes beyond just stealth. The B-21's efficiency and cost structure mean the United States can field it in numbers that make defense through attrition impractical. The Air Force plans to acquire at least 100 B-21s, potentially more depending on budget and strategic needs. Each aircraft costs approximately $700 million in current dollars. Expensive by conventional standards, but remarkably affordable for a penetrating stealth bomber. For comparison, the B-2 program cost over $2 billion per aircraft in then-year dollars. That affordability changes the operational calculus entirely. With only 20 B-2s, each aircraft is a national asset too precious to risk except in the most critical missions. Commanders plan missions around avoiding losses, accepting constraints on targeting and tactics to preserve the fleet. With 100 B-21s, the math changes. Losses, while never acceptable, are sustainable. Commanders can take calculated risks, strike more targets simultaneously, and sustain operations at a tempo that overwhelming defenses through persistence rather than single decisive strikes. The B-21's range extends this advantage. While exact figures remain classified, estimates suggest the aircraft can fly over 5,000 nautical miles without refueling, enabling it to strike anywhere in China from bases in Guam, Alaska, or even the Georgia, continental United States. With aerial refueling, the range becomes effectively unlimited, allowing the bomber to approach from unexpected directions, loiter in holding areas waiting for optimal strike windows, and return to distant bases where Chinese retaliation cannot reach. The weapons integration is equally impressive. The B-21 can carry the full range of American precision-guided munitions, from 2,000-pound JDAM bombs to AGM-158 JASSM cruise missiles to the new AGM-183 ARRW hypersonic weapon. The internal weapons bays are modular, allowing the aircraft to be configured for different mission sets without external modifications. A single B-21 could carry 24 small-diameter bombs for striking multiple individual targets, or 8 JASSM cruise missiles for long-range strikes, or a mix of weapons tailored to the specific mission. But the most feared loadout is likely a combination of conventional and electronic attack capabilities. The B-21 can carry standoff jammers that degrade enemy air defenses while simultaneously delivering kinetic strikes. This combination of electronic warfare and kinetic attack creates dilemmas for defenders that are nearly impossible to resolve. Do you shoot at the jammer, revealing your position to other attackers, or do you ignore it and accept degraded sensor performance? Either choice leads to losses. The operational concept for the B-21 in a China scenario is devastating in its simplicity. Multiple aircraft approach from different vectors, forcing Chinese air defenses to spread their coverage thin. Some B-21s carry electronic attack packages, jamming and spoofing radars across wide areas. Others carry kinetic weapons, striking high-value targets. Command posts, radar sites, air defense nodes, and logistics hubs. The bombers operate at medium altitudes, high enough to avoid most short-range systems, but low enough to use terrain masking when beneficial. Chinese interceptors vectored to intercept areas by increasingly unreliable. Ground control, find nothing. The B-21s are too small on radar to target reliably, and their electronic warfare systems create false tracks that waste interceptors and missiles on ghosts. Surface-to-air missile batteries designed to engage targets they can track reliably face an enemy that appears and disappears from their screens, never presenting a clear enough picture for launch authority. By the time Chinese defenses realize what is happening, the B-21s have already released their weapons and are aggressing. Cruise missiles launched from standoff range, 200 miles or more from the target, fly terrain-hugging profiles that make them difficult to intercept. Targets begin exploding across the depth of Chinese territory. Air bases cratered, command centers destroyed, air defense batteries silenced. The entire integrated network, built over decades at immense cost, begins to collapse as key nodes are eliminated. The psychological impact is as important as the physical damage. Chinese commanders, accustomed to operating in sanctuary behind their defensive wall, suddenly face an enemy that can strike anywhere, anytime, with impunity. The B-21 does not need to destroy every target. It just needs to create enough uncertainty that Chinese forces cannot mass, cannot concentrate, and cannot execute coordinated operations. The bomber becomes a strategic inhibitor, its mere presence in theater enough to paralyze enemy decision-making. Chinese attempts to adapt are hampered by the fundamental physics that govern radar detection. To detect smaller radar cross-sections, you need more powerful radars or radars operating at even lower frequencies. More powerful radars are expensive, consume enormous amounts of electricity, and are themselves large, immobile targets easily destroyed by standoff weapons. Lower frequency radars have even worse resolution, providing detection without the precision needed for targeting. You might know something is in a 10-kilometer box, but that is not enough information to shoot at it. Some Chinese theorists have proposed using artificial intelligence and multi-sensor fusion to correlate data from dozens of radars, hoping that aggregating many imprecise detections could create a targetable track. The concept is sound in theory, but difficult in practice. Each radar sees something slightly different, reported with different levels of confidence and different latencies. Fusing this data in real time, filtering out false positives, and generating fire control solutions fast enough to matter requires computational capabilities and algorithms that China has not demonstrated. Others have suggested passive sensors, infrared search and track systems, acoustic arrays, or even optical systems using cameras and image processing. But the B-21 operates at altitudes and ranges where these systems are ineffective. Infrared detection requires line of sight and is degraded by atmospheric attenuation and the aircraft's own thermal management. Systems. Acoustic detection works for subsonic aircraft at low altitude but is useless against a high-altitude bomber. Optical systems cannot see through clouds and have tiny fields of view compared to radar. The most likely Chinese response is to accept the problem as insoluble with current technology and focus instead on resilience, dispersing forces, hardening critical infrastructure, and building redundancy into command and control networks. These are sound measures, but they concede the fundamental point. The B-21 can penetrate Chinese airspace, and there is nothing China can do to reliably stop it. The fortress in the sky has a door, and the United States just walked through it. Allied nations have taken note of the B-21's capabilities. Australia has expressed interest in acquiring its own long-range strike capabilities, potentially including B-21s if export restrictions are lifted. Japan, facing increasing Chinese military pressure, sees the bomber as validation that investing in advanced capabilities yields strategic dividends that mass alone cannot achieve. Even smaller partners recognize that the B-21 changes regional dynamics, making Chinese military bases and infrastructure vulnerable in ways they previously were not. The economic dimension cannot be ignored. China has spent an estimated $300 billion over 2 decades building its integrated air defense system. The B-21 program, by comparison, will cost approximately $80 billion, including development and procurement of 100 aircraft. The return on investment is extraordinary. For a quarter of what China spent on defense, the United States built a capability that renders that defense largely ineffective. This is asymmetric warfare in the truest sense, achieving decisive advantage through innovation rather than matching the adversary resource for resource. Russian observers, initially dismissive of American stealth, have grown quiet as the implications sink in. If the B-21 can penetrate Chinese defenses, which are comparable to or better than Russian systems, then Russian airspace is equally vulnerable. Moscow has no answer to the B-21, and developing one would require investments Russia cannot afford. The strategic calculus that governed deterrence for decades, built on the assumption that bombers could be intercepted reliably, no longer holds. Right now, B-21 Raiders are in flight testing, accumulating hours, and validating systems across the full operational envelope. Production aircraft are being assembled at Northrop Grumman's Palmdale facility, with the first operational unit expected to achieve initial operating capability by 2027. Each aircraft that rolls off the production line is another nail in the coffin of Chinese air defense doctrine. The bomber that China mocked as just another expensive American program has become the weapon that makes their defenses irrelevant. The fortress they built to keep America out has become a prison that traps Chinese forces under a sky they can no longer defend. The mockery has ended. The radar screens remain empty, and somewhere over the Pacific a bomber flies that no one can see coming, carrying weapons that will arrive before anyone knows they were launched. The balance of power built on the assumption that defenses could defeat offense has been shattered by an aircraft that refuses to play by those rules. When stealth becomes absolute, when detection becomes impossible, the fortress becomes a target. And the nation that spent decades building walls just realized they built them facing the wrong direction. What do you think? Can China develop effective counters to the B-21, or has the strategic balance shifted permanently? Drop your thoughts below.